Legend has it that Imperial China was formed in the time of a great flood. The first emperor was Yu the Great, Yu the engineer, who fought back against the floods by building dams, by dredging rivers, and by building canals. He worked tirelessly throughout his life, and one day by the side of the river he found a turtle, and scratched into its shell was symbols of the magic square, exactly showing balance across the directions, horizontal, vertical, and diagonal. And since that time, the magic square has been a symbol of balance and purity and problem solving from ancient China. It's connected through the I Ching to what we know as the symbols of binary. And this is the first example of mathematical problem solving on Earth. On the other hand, the 6 by 6 magic square, 17 quintillion, 753 quadrillion, 889 trillion, 197 billion, 660 million, 655,632. Middle, well, the 5 by 5 has 275,305,224, and the 4 by 4 magic square has 880 solutions. I found that out last year, and when I heard that, I was like, wow, I have to investigate. So what's different about this maths channel, maybe to other maths channels, is that I always try and set myself a problem in every video and investigate the problem. But since this is the Summer of Maths exhibition, in fact, I'm going to give two pieces of advice for school teaching. The first one is the steps of problem solving that I go through in every video and every time I solve a maths problem. And the second piece of advice, which not everyone in the maths world agrees with, is that you should teach the vocabulary at the start of the lesson. Okay, so the solution space is all the valid guesses for a problem. In this problem, it will be all the 4 by 4 matrices with 1 to 16 inside it. The computational complexity is how many steps it takes an algorithm to solve a problem. Computer scientists measure this with equations. We're not going to use any equations in this video. A dictionary attack is when you just check every single option in the problem. In this problem, it would be all the possible squares with 1 to 16 inside. 16 times 15 times 14 times 13 down to 1. Too much to check. It's a ridiculous number. So we need to get the computational complexity down. That's all we need to know about that, really. Discrete optimization problem is a problem like the traveling salesman problem, or the closest string problem has had a lot of attention recently. A discrete optimization problem, you give a set of discrete inputs and you get a score from your input, and you're trying to find the best input to minimize or maximize your score. That's the vocabulary out of the way. So a maths investigation is maybe my favorite form of maths problem solving. It's different to a normal problem, like when I said, what's the area of an average triangle? I just used my knowledge of geometry and probability, whereas here I don't have a definite way to do it. The question is, can you spot the pattern? This is the first step of an investigation. You need to spot a pattern. The second step is you need to show the pattern is always true. The third step is that you prove the pattern algebraically. And the fourth step is that you extend the problem. The 0th step being that you have a problem in the first place. And it needs to be investigated because you don't know what the maths technique would be, which is, I was very happy and surprised to find out that 4 by 4 squares came in this category, because I thought I'd do it easily. A bit of thought about simultaneous equations or something. When I started to investigate 4 by 4 magic squares, it took me over an hour to get one. I was shocked by how hard this actually is. And you're not going to get to appreciate that because you're just going to see me do it here. But if you want to stop and try, don't bother. Just keep watching the video. Don't even stop. Just keep going. So I'm just simulating here what I did. And after some moving the squares around, I found I was writing totals in the rows and columns that were getting closer and sort of zooming in on 34. And this made me think, well, if I take the difference of each one from 34, I can sum the differences and get a score for each matrix as I go, that is how the distance that it is from being magic. And once you do that, you have a discrete optimization problem, because to get from one matrix to another, it's one move, it's swapping two squares, and every matrix has a score. So now I had spotted a form of pattern, so I used computer code. So what exactly was the pattern that I had spotted? Because when you spot the pattern, it has to be absolutely precise. Just like your question, find the 880 4x4 squares, has to be precise. So my pattern is this: you take you just randomly throw the numbers on, then you sum all the rows and columns. We're just going for rows and columns first, and then you will have some sums that probably won't, some sums for some, which probably won't be the 34, but occasionally they will, but they'll be higher or lower. So you find the row and column with the highest, the row and column with the lowest, and you draw across the grid and find the high square and the low square. If the high square is big and the low square is small, you can switch them, and your matrix distances from the magic square will go down, usually. Unfortunately, when you start getting towards 0, it might not go down. And also, in some weird situations, it won't go down. So you need to check that before you switch. If it doesn't go down, you can have a secondary backup algorithm, or you can just randomly throw again. I just randomly, on paper, I did more. And I think that if you have a big square, like a 10 by 10, it will usually work, at least to get to semi-magic. But on the 4 by 4, it doesn't always work. And even if it does work, you then have to set up a similar thing with the flicking rows and columns to get the diagonals. And what I found from this experiment on the computer was you had to do it loads of times to get a handful of magic squares. And because they're random, you're not necessarily going to get 880, even if you do it thousands and thousands of times. So although I had successfully spotted a pattern and I had checked the pattern for correctness, the pattern did not solve the complete investigation. So it's back to the lab again. Oh, there goes gravity. What's the new plan? More investigation, more scribbling on the paper that you don't want to see. And I noticed another fact with my technique for getting them. I had quite a few, and all the ones I looked at displayed this property that you could rotate them so that at least in one direction their lines would have quartets, by which I mean you've got 1, 2, 3, 4, the small numbers, 5, 6, 7, 8, the big small numbers, 9, 10, 11, 12, small big numbers, 13, 14, 15, 16, the big numbers. So there's 4 types of number. And if you just color them, say, to make it obvious, you always get one of each in the lines of the squares that are magic. You might have to rotate it, but the rule will never be broken. So I don't know that that's true, but I've spotted another pattern. So now I can start writing code again, and this time I write code not to throw them randomly. I start off by running the code. Well, I had to decide how to do this. By the way, you're not going to see this, but when I did the whole thing, I subtracted 8.5. So I'm always, 1 is minus 7.5 and 16 is plus 7.5. You don't have to think about that. But I had the 2 sides on the grid, and I decided to fix the plus 7.5 because I always stay positive. And so I moved the others to the 24 possible permutations and then figured out which 2 could go in the middle, but I'm just always going low to high. I'm not thinking about the columns. And I got all the possible rows that can have this property. Then I had to find the columns. So it turned out there were exactly 105 of these, which that was non-obvious. So already it was getting tricky, but it now got much more tricky. I had to find all of the columns, and I did this. I didn't want to start moving the numbers around, even though I am the number juggler. I wanted it to be more visually geometric, so I put crosses, circles, and squares shapes on top of the grid, and those shapes would represent choosing one from each line. But by doing that, I could see which shapes worked more often, where if I just moved them, I couldn't see what I'd done so easily. Where by putting the grid of shapes on top, it shows me what grid works and what doesn't. Although I still couldn't figure out what ones would work and why they would work. So I had to go through this, searching exhaustively for the semi-magic squares by moving through each line at a time and finding all possibilities. And finally I did this. There was 419 semi-magic squares. 427. It's like 420. You have to do the same thing again. But the second time, when you choose from each row, you also have to choose a different option. So for this time, I have juggled the numbers, but so you can see it more clearly. But you can't choose the same column and you can't choose the same symbol twice. This became confusing, and you can see on the graphic sometimes it does choose the same symbol twice, and you can choose the same symbol twice if you have extra lines going down because you're choosing diagonals, so you only have to choose two. So as long as one doesn't overlap with another one, you could choose those two. So you can choose the symbols twice. There are further complications to this. The way that I'm searching will not, apart from not respecting different reflections and rotations, which we don't want, it also won't respect certain other things that we do want. So the transformations in geometry are rotations, reflections, and translations. And you might think, well, we can't translate a magic square. Even if you move the top line to the bottom line, it's going to mess up, isn't it? But you have to think there are actually three kinds of magic square. The ones that what I called the normal magic square, you've only got the one diagonal meeting. There are what I call double magic squares, where the off diagonals also create 34. So those you could translate them one and get another magic square. There's something else called a perfect magic square. And I've seen YouTube videos say there's only one perfect magic square. And it's all the rows, all the columns, and all the diagonals, including the third diagonals, will add up to it. And of course, you can translate this 16 times and rotate and reflect each of these 16. There's more than that, actually. There's three. I've fully researched this. There's three perfect magic squares, so there's 48. So when you're searching, you have to kind of check each thing. So I realized that each square that I found, I would have to check 16 times to make sure if there was extra translations available. So, but my main concern wasn't how long my check was taking, although I was taking far too long. The main concern was not finding all of the squares. It was hard. I couldn't get it, to be honest. I gave up after some time, and when I came back to it, I went back to my original plan with the random numbers and just ran loads and loads of the random ones. And then I made a class that could compare the ones that I was finding with the random ones that I had found. And there was some magic squares in the random ones that weren't in mine. And I investigated further. I found that they were in the semi-magic square. So it was the diagonal search that was going wrong. And if you've been thinking and paying attention, then you might be able to know what I did next. So if I just took one of these semi-magic square grids that I found and I wanted to check all the possibilities, I would have to switch all the rows and all the columns around. But I realized since at the end I'm translating for 16 places, I don't have to switch the first row and the first column to check all the possibilities. I only have to switch the 3 rows and 3 columns, which is 6 and 6, which is 36 possibilities for one magic square, and then I'll be checking the 16 translations. So remember the vocabulary at the beginning, the dictionary attack. 36 possibilities for each of the 427 grids of semi-magic squares. I could just check all of them. It was easy. It's less than 16,000 squares to check, and suddenly trying to get this diagonals, columns, PlayStation thing to work, it was completely unnecessary. I was doing it for months. No need. You could easily do this with Dictionary Attack. I was wasting my time. And yeah, one magical evening, I felt in touch with the universe and history and the mathematicians of the past and the alien mathematicians on other planets. We all find the same 880 magic squares. So here they are, all 880 4x4 magic squares in 88 seconds. If anyone says to you, have you seen all 880 4x4 magic squares? You can say, yeah. So there's 2 parts to solving this algebraically. I searched a bit at the beginning before I started the investigation. I thought there must be some way with simultaneous equations and matrix algebra, but I couldn't find it, so I stopped searching. And then I did the investigation without any help from AI or anything. I wrote the whole code myself. Now it's complete. I allow myself to search, and it's a good job we're allowed to because I cannot Google this myself. So I'm using ChatGPT, and it's told me that use binary coordinates and you put them into a certain group of Boolean functions, which will give you, for each square, it will give you 4 outputs, and you use those 4 ones and zeros to create the number up to 16 using binary. So with these special set of Boolean functions, which are called the 4 balanced linearly independent binary affine functions. But to get all the magic squares, you must use all the possible permutations of these special 4 Boolean transformations, which is 55,296. So once you understand this Boolean binary way of doing things, it completely explains my four numbers quartets in one line. It's the same, it does explain it, but that's a story for another time. It won't fit in this video. So that's still quite a lot. And what really fascinated me about this was that there's no matrix algebra way, but there is a binary way which connects to the original Chinese way of doing things. So this is fascinating because this is modern computer science techniques, and the paper ChatGPT gave said in 1982 from the Royal Society that was for the 4x4. The 6x6, that big number I said at the beginning, was only found in 2024. That's last year as I'm saying this, and it was done through searching. It had to be searched exhaustively. So we still don't have a complete understanding of magic squares at all. We need to fully understand the solution space if we're ever going to find out how many there are for 7x7, 8x8 or more, because it's too many. The size of 7x7 would literally fill the internet, just the solutions. So you'll never do it with an exhaustive search. So my further investigation is going to be, how do you find the total number? So what we can look at is what I was saying earlier. If you take these quartets, the numbers 1 to 4, 5 to 8, 9 to 12, and 13 to 16, there's one of those numbers in each line of a magic square. Now I've found them all, we can say there's 105 possibilities for those squares that can be made with those quartets. Only 30 of those possibilities contain semi-magic squares, which can then be made into magic squares. And some of those 30 have a lot more than others. There will always be 4. If there's 1, there will always be 4. So 4 is the minimum. But you can see in this grid, also as I mentioned earlier, there's normal, double, and perfect. So where you see 3 together, that is the normal first, then the double, then the perfect. So some numbers, some setups have a lot, some don't have many, some have the different types, some only have normal, some normal double, perfect. Some can be rotated so they'd be in 2 places. But I think researching this and finding the explanation of this will lead to the understanding of magic squares. So this is my discovery. I don't fully know why it looks like this or why when it fully zooms out it looks like Chinese characters, but this is what I've discovered. That is what I found, and I'm still curious to know more. Why is there 3 perfect squares exactly? How many perfect squares are there for 5 or 6 or 7? What else is going on? Can I make a 16 by 16 out of my 4x4s? Not for the end of this video, I can't, I'll tell you that much. But I hope you enjoyed Summer of Maths. I had a great time making this. I hope you enjoyed it, and I'm looking forward to watching the other videos. I haven't had time yet. But thank you everyone who's involved. Thank you, Grant. This is amazing. You know what to do.